Assalamualaikum and salam sejahtera. Our topic today is on filter, where we're going to discuss on low pass filter. On this short presentation, we're going to discuss on how low pass filter works in filtering signals. Second, we're going to do some derivation based on low pass filter circuit. And lastly, we will go through one example on how we can design a low pass filter based on specific requirement. So how low pass filter work? Low pass filter work by passes signals that having frequency lower than cutoff frequency. And it will attenuate signals that having frequency higher than cutoff frequency. Looking at this characteristic behavior of low pass filter, we can see FC here is our cutoff frequency. So any signal that are lower than cutoff frequency, for example at this region, is having gain equal to 1, meaning the signal is passes through. While for this region, the frequency is higher than cutoff frequency, we can see the gain will be smaller than 1 and eventually goes to 0. That means this signal is filtered out. So it is very much depend on the value of cutoff frequency here. And this cutoff frequency will be depend on the filter design. Meaning we are the one that going to design the value of cutoff frequency. This is the circuit for low pass filter. This circuit is also known as simple RC filter, where R is resistor and C is capacitor. So we can see there is one resistor here and one capacitor in this circuit. This is our V-in, the voltage input to the filter, which representing the voltage for our signal. And this is our voltage out, which is the voltage output after the filter. If the signal is having frequency smaller than cutoff frequency, then we get V out equal to V in, or gain equal to 1, which means the signal is passed through the filter. But if the frequency is higher than cutoff frequency, we will see that V out will be smaller than V in, or the gain is smaller than 1, which means that our signal has been filtered out or attenuates. So now we're going to do some derivation based on our low pass filter circuit. But before that, we need to go to revisit the basic concept of voltage divider. This is because we can see that there is a similarity between our low pass filter circuit with voltage divider circuit. So due to that, we're going to use an equation based on voltage divider and use that in the derivation of a low pass filter circuit. So in general, based on load circuit of impedance in this voltage divider circuit, we can see that there are two impedance, which is Z1 and Z2. So the equation for voltage divider circuit will be Z2 divided by Z1 plus Z2 multiplied with our V in give our V out. Please note that Z is impedance, which can be a resistor, can be a capacitor, can be inductance components. Okay, let's derive the equation for low pass filter. Based on the voltage divider circuit, we have the equation of V out equal to Z2 over Z1 plus Z2 V in. So looking at our circuit here, so this is ZC and ZR. So replacing that into our equation, we have V out equal to ZC over ZR plus ZC V in. So the load for resistor ZR is actually the value of resistance itself, while for ZC it is 1 over CD, which also equivalent to 1 over CS. We do know that in frequency response, S will be replaced by J omega, making that our ZC will become 1 over C J omega. Let's replace that value into our equation. Okay, so now we're going to have 1 over C omega divided by R plus 1 over JC omega, which can be simplified to become 1 over 1 plus J omega CR. In terms of magnitude, because we're interested in the magnitude value, okay, will be equivalent to 1 over square root 1 plus omega CR square. Let's change the term omega into frequency, which is omega is equal to 2 pi f, meaning now our equation will become 1 over square root 1 plus 2 pi f CR square. The equation that we have derived gives us the output to input voltage ratio for any signal frequency. For a specific value of C and R, we will be able to determine the value of output to input voltage ratio by replacing the frequency value into the equation. We already know that cutoff frequency is a parameter that determines the characteristic of low pass filter. FC can be calculated using this equation, where it will depend on the value of R and C. Replacing FC into equation 1 here, we get an equation that normalizes to cutoff frequency. Let's calculate what is the gain or output to input voltage ratio when the frequency is at cutoff frequency. So now we're gonna replace this F here to be FC, meaning now our gain will become 1 over square root 1 plus 1 square, which will give you 0.707. This graph shows the response of low-pass RC filter as a function of frequency ratio. We can see here at the x-axis here, it is representing F over FC, and y-axis representing the output to input voltage ratio, or sometimes we call this as gain. Okay, we have calculated before when F equal to FC, which is for a ratio 1 here, the value here is 0.07, approximately 0.707. Okay, so meaning if the frequency is at cutoff frequency, the gain will be 0.707, meaning it will reduce some of the voltage. But if the frequency is 10 times smaller than a cutoff frequency, because this is a log graph for the x-axis, so we can see here 10 times smaller than FC, the gain here is 1, meaning there is no attenuation happen if the signal is lower than 10 times of cutoff frequency. And if we see here, this is when the frequency is bigger than 10 FC, 10 times bigger than FC. So we can see the signal has been attenuated to 0.1. Okay, only 0.1% of the input will be passed through the filter. As the frequency increase further, the gain will eventually goes to 0. So this is the characteristic for low pass filter, where we said that for a frequency smaller than cutoff frequency, gain is 1, meaning it is passed through, the voltage input will be passed through the filter. But if the frequency is bigger than cutoff frequency, then the signal will be attenuated. Therefore, for a design method for low pass filter, we actually need to choose a proper value of C and R so that it will give us a specific value of cutoff frequency. In order to choose the value of C and R, normally for capacitor value, we choose a value between microfarad and picofarad. And as for resistor, we choose a value of 1 kilo ohm up until 1 mega ohm in order to avoid noise and loading effect. And of course, we have to use a standard resistance value. By choosing C and R, we will be able to determine what is the cutoff frequency of our filter. Therefore, we will be able to determine the behavior of our low pass filter. Okay, let's look onto this example. I hope you will understand on how to use the equation for low pass filter in order to solve any problem related to low pass filter. Okay, so what do the information in this example tell us? Okay, it said that okay, our measurement signal is up until 1 kilohertz, meaning the frequency of our measurement signal is up until 1 kilohertz. Okay, but at 1 megahertz, there will be a noise affecting our measurement signal. So therefore, we need to design a low pass filter where we want that filter will attenuate okay, at 1 megahertz here, it will attenuate the noise up to 1%. Only 1% will pass through the filter, while another 99% will be blocked. So we need to design a low pass filter, meaning to choose a correct, not a correct, a suitable value for cut-off frequency, so that at 1 megahertz only 1% is passed, and 99% will be blocked. And for the second part here, okay, what is the effect on the measurement signal at its maximum of 1 kilohertz? For our low pass filter, we're going to see what will be happen here. Either it is 100% pass or 99% pass or 90% pass. This is actually equivalent to gain equal to 1, gain equal to 0.999, and then gain equal to 0.9. So we're going to use the equation for low pass filter. Okay, this is the equation: 1 over square root 1 plus f over fc square. From the requirement, it said that at f equal to 1 megahertz, the gain must equivalent to 0.01. Putting the information into the equation, so therefore the equation will looks like this: 1 plus num over fc square. Looking at this equation, the only unknown is only fc here. So therefore, we'll be able to solve for fc. If you solve the equation, you get fc equivalent to 10 kilohertz. So for fc equal to 10 kilohertz, we know that 10 kilohertz will be equivalent to 1 over 2 pi rc. So now we just need to choose a value of r and c that give us 10 kilohertz. So let's say that we choose r to be 10 kilo ohm. So therefore we will be able to calculate that c is 1 over 2 pi 10 kilo ohm multiply with 10 kilohertz. Therefore, C will equivalent to, that will give us capacitance is 1.59 minus 9, or 1.59 nanofarad. So the design for our low pass filter will look like this. We have a resistor, a capacitor to the ground, and this is our V out, our V in. Then the value for capacitor is 10 kilo ohm, and the value for the capacitor is 1.59 nanofarad. So as for the second part, okay, we need to determine what will happen when the frequency is equivalent to 1 kilohertz. So now again we're going to use the same equation. Again, the magnitude of gain equivalent to 1 plus f over fc square. So we know the frequency here is 1 kilohertz and our FC is 10 kilohertz. Okay, we already determined that our FC is at 10 kilohertz. So putting the information into the equation again, now we're going to calculate for gain, which is 1 over 1 plus 1 kilohertz over 10 kilohertz square, which will give us gain equivalent to 0.99. So we can say that the gain is approximately 1. So meaning here at 1 kilohertz, there will be no attenuation happen. All the signal will 100% pass through. Okay, so therefore our cutoff frequency is acceptable, meaning we don't want to lose any information at 1 kilohertz because we know that our measurement is lower than 1 kilohertz. So meaning it is safe to have a cutoff frequency at 10 kilohertz so that our measurement signal will 100% pass through. So therefore, that is how we design a low pass filter based on the requirement given in the example, where it said that the filter must able to block around 99% of noise signal at 1 megahertz. So from that requirement, we calculated that our FC must be at 10 kilohertz, and when we check at 1 kilohertz, we get that all the signal having frequency lower than 1 kilohertz will be 100% pass. Okay, so hopefully you will understand on how we solve the problem using the equation of low pass filter.